Let's begin. Now I will put student associated with the Center for Systems and Control at IT Bombay. And I'm also EE98. So let's begin today's tutorial session. Yeah, I'm just trying to reshare my courses. Last time we studied about state transition matrices. So first of all, we'll study two ways to compute a state transition matrix. First one is evaluation of STM. So there are two ways to do so. One is by diagonalization, and the other one is through the Cayley-Hamilton theorem. Then next one is using Cayley-Hamilton theorem to calculate some powers or inverse of the matrix A. So this is different. Cayley-Hamilton theorem, but let's say to compute some function of A or A inverse. And then we'll look at controllability. So there is the Kalman test and Gilbert's test. Okay. And then finally, we'll take a quick look at stabilisability. Okay. So let's look at the first section, evaluation using diagonalization or the similarity transformation. The first is good. So this is easy. We have already looked how to diagonalize a matrix. So recall that e to the power 80 for some square matrix A is given by e to the power 80 is p e to the power lambda t inverse, where P is M or the modal matrix, eigenvalues matrix, eigenvalues or the diagonal matrix. Or a normal if the eigenvalues are repeating. Okay, so one example is for distinct eigenvalues. This is simply lambda 1, lambda 2 till lambda n. Mhm. Okay, so this is n by n. And then zeros here. Okay, so let's start with a simple question. Consider the system x dot equals 0, 1, minus 2, minus 3, x, and the initial condition is simply 0, 1. Okay. So we can evaluate the state transition matrix using this, but we'll try with the eigenvalue test first. So let's see. The characteristic polynomial is a minus lambda I and superminent. This is minus lambda, minus 3 minus lambda, and minus 2. This is 0. This is 3 lambda plus lambda square plus 2 equals 0. And I think this is lambda plus 1, lambda plus 2. Okay. So the eigenvalues are minus 1 and minus 2. So we already know what the diagonal matrix is going to look like. This is minus 1, minus 2, 0, 0. And now we want to pre-multiply by p, post-multiply by p inverse to get e to the power 80. And this is also exponential of this. So this is simply e to the power minus t, e to the power minus 2t, 0, 0, p inverse. So to get p, we need to find the eigenvectors for each of the eigenvalues. Let's do that quickly. So for lambda equals minus 1, this is a minus lambda I times v equals 0. So this is plus 1 and this is minus 2. So you can observe that this would give the same equations. It's just a scalar multiplication. So this implies that v1 plus v2 equals 0, which is v1 equals minus v2. So the eigenvector associated with minus 1 is, let's say, for some constant k equals 1, this is 1 and minus 1. Sorry, this is, yeah, this is good. Okay. For lambda equals minus 2, a minus lambda I is, okay, this is 2, 1 minus 2 and minus 1. Okay. So this acting on v1, v2 equals 0. Okay. So one of the eigenvectors is, so v2 is, let's see, okay, v2 is minus 2, then this becomes 1. So p is, because we have already fixed what the diagonal matrix should look like, p is going to be the eigenvector for lambda equals minus 1, and then lambda equals minus 2. Then the inverse is easy, so it's minus 2 plus 1. So e to the power 80 in this case is 2, oh sorry, 1, 1 minus 1 minus 2, e to the power minus t, e to the power minus 2t, and then p inverse. Okay, so this is easy. Okay, let's see. So this is 2 e to the power minus t minus e to the power minus 2t. And then plus 2 e to the power minus 2t. This is a state transition matrix for time greater than equal to 0. And now x of t is this. And the initial condition was 0, 1. Okay, so this is just answer. Well, yeah, there were 4 entries there. So then this is e to the power minus t. This, this is incoming. Okay, so these entries times 0, 1. That would be x of t. So this is e to the power minus t. And then this one. Okay. So note that this was zero. You can verify using the initial expression, Laplace inverse of Sm minus L inverse. You could also try taking EXPM in MATLAB and find out if this is the same answer. Alright, so let's look at another question. Find e to the power 80 for x dot equals 0, 1, 0, minus 2, x1, x2 for these initial conditions. So I'll just write down the eigenvalues and the matrix quickly. You can figure this out later. So lambda is 0 and minus 2. And P for this case is 1, 1, 0, minus 2. Then you can figure out what P inverse is. And I write down e to the power 80 directly. So this is e to the power 80 inverse, which is half okay. So xt is e to the power 80 times 1, 0. And this is simply. So what does this mean? So the initial condition and solution at any given time is the same. So the solution is constant. So say it started from this is t, this is x of t. This is in 3 dimensions. X of t has 2 coordinates. It starts from 0.10 here at time t equals 0 and then stays here. So this is when there is no input. Just observe that B in this case is 0. So if there is no input in the system remains in the initial condition. So you can give any initial condition. So it could be, so no, for this case it is. So if it is a some 1, 1, then it would become independent on time. Now let's crack another question. This is for a third order system. Yeah. Yeah, I think. Okay. So if it is, for example, the Jordan normal form is lambda 1, 1, 0, 1. So let's say there are two eigenvalues of a second order system which are repeated. Right? This would be the diagonal form of that system. So e to the power jt in this case would be e to the power lambda t 0 e to the power. And now we need to find out p and p inverse, right? To find out e to the power e. So in that case, so the first eigenvector would be using a minus lambda I times v equals 0. And the second one is just a second, I have to check. So I think it's mm, one second, one second. So I think it's d by d lambda, and then you take. Okay. So this is correct. This is, I think I have to check this out one second. So the problem is to find the other eigenvector for the same eigenvalue so that P inverse also exists. So second. I'm just trying to find an example. Yeah. Yeah. So what is singular value decomposition is for alpha? It's movie, right? Yeah. Okay. Just I don't know. I think the best way to check would be you could just compare. So for like a simple matrix, you can find out the state transition matrix and then check if it comes out. I'm not sure if it does. I have to check that. Mm. Just one second. Just a second. Mm, I think we take a derivative somewhere, but I'm just have to check this. Just 1 second, I'm just looking at an example. Mm, why do you want to use singular value decomposition? Is it easier or you can find out easily using MATLAB? Is there a reason that you Mm, yeah, okay. Okay, okay, fine, that's it. Mm, yeah, that might be true. It may not always hold, but maybe in some particular cases that would be true. Mm, mm, just said. No, I'm just trying to find some example. I think most of the examples online are just for distinct eigenvalues, so it's a bit. Mm, I think I'm finding it. It's just Just so if we collect this equation for every lambda, so I didn't find an example, so we'll just try it in the general form. This is for one eigenvalue and its corresponding. Okay. And we want to get the B matrix, which is, let's say, V1, V2 up till Vn. And whenever we apply A to this is simply AV1, AV2, and by the definition, so this is simply going to be Vn, which is this is lambda times V, so this is, let's say the first eigenvalue was repeating, so lambda 1 is equal to lambda 1, lambda 2, lambda 3. This is going to be n by n. So going to multiply with V, so I think this would be you just have to take care of the dimensions. So for the first eigenvalue, this is AV1 equals lambda 1 V1, AV2 equals 1 plus lambda 1 V2. A, for example, any Vk for k greater than 2. So those are the distinct eigenvalues from 2 to n. Sorry, 3 to n. This is simply lambda k Vk. This is what we have been doing till now. This is A minus lambda k and Vk equals 0. And then we solve for Vk. But if we have repeating eigenvalues, for example, the first one, and we want the second eigenvector, so this would be A minus lambda 1 I V2 should be equal to V. So you find this out using the general expression, and then you plug this into the second one to get it. And this way, this would be P, and P would be inverted. So we can still do P and P inverse. So P and lambda T inverse. And e to the power lambda T in this case is, for the simplest case, it would be this. For example, if it's a third order system, there are two eigenvalues which are repeating. So in that case, the Jordan normal form would be lambda 1, 1, 0, lambda 1, and lambda 2. We can find out the eigenvectors. So this would be e to the power jt. So this is very easy to compute. This is I plus gt plus square t square 2 factorial and so on. So if you club these terms, you'll find out that this is given by e to the power lambda 1t. This is e to the power lambda 1t, and then we can just multiply by p and p. So there would the only difference is that there is t here. So if it was 3 repeating loops, this would be lambda for just let's say third order system with repeating loops. This would be lambda. This would be the Jordan curve, right? Or the Jordan curve. And then in this case, e to the power jt would become. So this remains the same. This becomes t to the power lambda t, which is actually is it t square? Just trying to find the most general form which exists for any order repeating bits. So, this was yeah, for a third order system, you mean, right? If it's two repeating bits. In this case, right? Yeah. Then it would be lambda 1 and lambda 2. Yeah. We have to calculate this, but this comes out to be e to the power. This is so in general for this, if you go along with this, it will be e to the power lambda t to the power lambda t. Then it's factorial, right? Because we are collecting terms from this one. So it would be t square by 2 factorial e to the power lambda t, t cube by 3 factorial, and so on. This would be the first rule. And then you would shift it. So shift this here, shift this here, and then keep on shifting it till you get that n by n Jordan number. Yes. Okay, so let's see. Something we're talking about in third order system. Yeah, let's see. Question 3. X dot is 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6. And we also have an initial condition. X of 0 is the vector 0, 0. So before beginning to compute into the power 80, let's first observe that this is in the CCF form. And last time we looked at a random mode matrix. I'm just going to write the expression. So if a matrix is in the CCF form and we have three distinct eigenvalues, then the similarity transformation is this. Lambda 1 square, lambda 2 square, lambda 3 square. And using this transformation, we can transform A into a diagonal matrix, right? So, let's see why in this case is 1, 0, 0. That is fine. So our job is to find out lambda 1, lambda 2, lambda 3. If these are distinct, we could do this. And then find what is P is. So let's see if characteristic equation in this case is 0. This is minus lambda basis. So I think you can calculate this, right? Lambda 1, minus 1, minus 2, minus 3. We have already looked at this example in previous sessions. So you already know what P is. 1, 1, 1. So you can calculate P inverse then by any of the methods we discussed in the tutorial sessions or using MATLAB. That's what's okay. And then you know what is e to the power 80. P, this is P. Now the next section is to compute the state transition matrix using the Cayley-Hamilton theorem. So state transition matrix. So this is the theorem states that every matrix of size it's n by n satisfies its characteristic equation. Okay, so let's see. This question 4. So if you know what A is, then we have to find out what is A square, A cube, or any of power of A. Let's say it will be 100. Or we could also find out what is A is. So we have been given A through its characteristic equation, that is lambda squared plus 3 lambda plus 2 equals 7. So if we need to calculate parts of A, we don't start with A, we start with its characteristic equation. That's it, right? So what do we do is substitute in this. So A squared plus 3A plus, and this is going to be identity matrix. So A squared in this case is minus 3A minus 2I. Then we need to find out what is A cube. So A cube is this, which is minus 3A squared minus 2A. So one of the main features of calculating STM using Cayley-Hamilton theorem is that we reduce all the parts of A to the ones given in the characteristic equation. So we can still reduce this, right? So this is the basic one. We can reduce for A to the power 4, which is A cube. Then we do minus 3A cube minus 2A square. and then we substitute for A. So it's 9A squared plus 6A minus 2A squared. So we reduce everything to the powers which are available to us to this characteristic equation. And now if we want A inverse, that so let's start with the characteristic equation. This is A squared plus 3A plus 2I equals 0. So let's assume that A is invertible. So we can multiply by A inverse on both sides. This is A inverse squared plus 3 plus 2 equals 0. This is simply A plus 3I plus 2A inverse equals 0. Simply implies that A inverse is minus half A plus 3. So this is a very neat trick because now we don't have to find out what A square and A cube are. We found out A inverse through just so now we have to find the polynomial. Let's get n of A and A to the power 4 plus A cube plus A squared plus A plus A. So A is given to us. A is 0, 1, 2 and 3. So if there are very high powers of A, the first guess should be that we should use the Cayley-Hamilton theorem so that we don't keep on multiplying A 4 times or thrice. So let's figure out what's the characteristic equation. This is it. So it's minus lambda, it's 3 minus lambda. Okay, so let's see that according to the Cayley-Hamilton theorem, this becomes 3A minus 2I equals 0. Just a second, I think this is minus 2, so and now we need to find out, we already have A square, so A square is minus 3 plus 2I. A cube becomes minus 3A square minus 2A. And then A4 is times A cube. So let's substitute A cube and A square. So this is minus 3. So this becomes plus. I think for this we could just have simplified at this stage. So actually, let me do that first. A cube is minus 3 minus 3A minus 2I. So this will be simpler. So this becomes 9A plus 6I minus 2A. Now A4 is this. A to the power 4 becomes 7a square plus 6a. And then we can substitute for a square again. This is 7 minus 3a minus 2y plus 6a. So there is, it's left calculated everything. Yeah, okay. So minus 49 and minus 21 plus 6. It becomes minus 15. Just check this once. Okay, so now let's substitute all of these in NA. This is a to the power 4. That's a cube. 7 8 plus 6, right? A square plus a plus 1 plus a plus 9. So this has become considerably easier to calculate. So let's calculate terms in A. This is this. The green ones are identical. Okay, so we have so this is minus 10a. Just and then if identity matrices, these minus 14 plus 2 is minus 16. This is minus 10, so this is minus 9. And so this is minus 10. You already have the matrix. 0, 1, minus 2, minus 3. So this is minus 9, minus 10, 20, minus 9. Right. So this is the evaluation of the polynomial. So let's recall a few concepts before moving on to the other question. So recall that this is the characteristic equation for an nth order system. This is I think degree is greater than 1, right? Because this was a 4-degree polynomial. I don't understand what you're asking. Is that it? Means that we have reduced this to this using the Cayley-Hamilton theorem. That is all. So if we didn't know, we have to figure out what is 8 to the power 4. We will just keep on multiplying. This is a 4-degree polynomial. But this is a matrix polynomial, so this is an 8. So this is minus 8 or just a minus lambda. This is some lambda to the power n plus alpha 1 lambda to the power of minus 1. The last term would be alpha. So I have chosen coefficient such that this added with this equals 0. This is 0. This is the characteristic polynomial. And using the Cayley-Hamilton theorem, This means that delta A e to the power n plus till alpha n times I is 0. It's a simple procedure for evaluating functions of matrices. So let's say that function is some f of a, and this can be written as alpha COI plus e and so on. Or in terms of lambda, this is lambda naught plus lambda, sorry, alpha 1 lambda. Let me just write this in terms of some other coefficient. E naught C1 lambda. So if we had f of a and we substitute any eigenvalue of lambda, we get, for example, this function. And if we divide by the characteristic polynomial delta lambda, let's say this is in some general form, Q lambda plus G lambda over delta. So this is some general form where this G lambda is. So if this is the remainder of a function like this, let's say that this also looks like some polynomial expansion. This is G lambda equals maybe with some other coefficients, beta 0 plus beta 1 lambda and so on. So let's say it was an n degree polynomial, and if it's a remainder, you can say that this goes till n minus 1, right? Because the other power is in Q lambda. So if we just cross multiply by delta lambda on both sides, this is Q lambda delta lambda plus G. And let's assume that we have distinct eigenvalues. So this would still work for repeating eigenvalues, but let's assume for now. Assume distinct eigenvalues for A as lambda 1, lambda 2, and lambda n. This means that for every lambda, this would be 0, right? Because this is the characteristic polynomial. So this means that f at any lambda I is simply G lambda. So the remainder term, beta 0 till beta, I think this is n, this would be n minus 1. Now can be determined by the equation f at lambda I equals G at lambda I for each distinct eigenvalue. And if we have lambda I, then again we have some other reduced polynomial G. So a function of polynomial A could be reduced to some n minus 1th order polynomial G. And These are n minus 1 coefficients. So we write down this for all the eigenvalues. We get a system of equations and then find out what beta naught to beta n minus 1. And then we also have a case for repeated eigenvalues. So like 2 for repeated eigenvalues. For repeated eigenvalues, we use derivative. Let's say some lambda k is repeating mk times. This means that d by d lambda k this evaluated at lambda equals lambda k is 0. And if it repeats mk times, so let's say this is the jth order derivative, and j goes from 0 to okay, so this is to find out what these beta naught to beta n minus 1 are. They are repeated eigenvalues. So one of them, the first one would be if we just substitute f lambda I equals g lambda. Let's say that lambda was minus 1, minus 1, minus 1. So the first coefficient or just the first equation would be this one, and this would be beta naught plus this is just 1, beta 2. And this is some known function which we have to figure out. And then we need we need 3 equations to solve for beta naught, beta 1, and beta 2. So the other 2 equations comes out from this derivative. So we already have the characteristic for the element, let's say, for the A matrix. And then we do this. So this is if I d lambda of delta lambda. So this is not x, this is lambda squared. And lambda equals minus 1. This is also same. So this means that okay, so just to recall, we had this q lambda and if we take any other derivative on both sides, this would be 0 because of these two conditions. This means that d lambda g lambda. And for the second order derivative, there would be another condition. Again, both evaluated at that repeated eigenvalue minus. Okay, so let's look at a question. This is really confusing. So, question 6. Find a to the power. Okay, so I'm going to write down the function. F of a is a to the power 10 for a matrix A given by again 0, 1, minus 2, minus 3. Okay, you already know the characteristic equation, which is what this is lambda square plus 3 lambda plus 2 equals 0. This means that we have a square plus 3a plus 2i equals 0. Eigenvalues are distinct. So this is minus 1, minus 2. And now we have just looked at a procedure on how to get f lambda using some reduced order polynomial g lambda. So let's see how that goes. So let's see that f lambda, the lambda could be minus 1, minus 2. So it's g lambda. This is given by I plus I, which beta 1 Why? Because this is a second order system and the general expression was beta naught plus, sorry, this is lambda. So now our job is to figure out what are beta 0 and beta 1. This is simply this. Okay. The goal is to find so f at lambda 1 is this one with the 110 and other one is, so let's just keep it this way. So yes, this is beta 0 minus 2 beta 1. So you can solve this system of two equations to find out what are beta 0 and beta 1. So let's just do this quickly. Okay, so this is 1. This means that beta 1 is 1 minus this is, and then just simple beta 0 is 1 plus beta 1. So 2 minus 2 that are 1. Or just simply 2 minus 2 content. So I'll just write this. Yeah. Yeah, this one. Yeah, we'll get another. Sorry, can you just repeat this? I think the connection on my side is unstable. So yeah. Okay. Yeah, that's true. So we'll get some more equations too. So then in this case, F A is G of A is beta 0 plus beta 1 A. This is 2 minus 2 to the power 10 times identity. Right. So in this case, we did not use exactly the Cayley-Hamilton theorem because then we would have to keep on multiplying both sides and get all the parts of it. In this case, we reduced it to a lower order polynomial. Okay, so now you know how to calculate okay, so A is already known. Let's say A squared, A cubed, A to the power 10, and so on, right? You can just plug in that this is the polynomial and you can find out what this is. So if we know all the powers of A, theoretically, if we can just keep on computing these, then we know what this is, right? Because this is simply I plus AP, then and so for each f of A, this would be, let's say, f1 of so this one. This one would be first function f1 of A equals a squared. Then maybe this is some third function e to the power n and so on. And if you can keep on clubbing these terms, you'll find some simpler expression which would exactly come out to be the state transition matrix. So we looked at, I think, three ways to compute state transition matrix. One is the Laplace inverse. One is using diagonalization or conversion to Jordan normal form. And then the last one was to use the Cayley integral. So it's there and understand. Okay, now you. I think usually if we have a complex system, we'll just move on to MATLAB, but it's nice to look at some of the ways as well. So, uh, controllability matrix would be the Kalman matrix, right? And that requires a square and all the polynomial functions of it. Okay. Yeah, I see. I see. That's nice. Yeah. So consider a system x dot equals ax, where a is 0, 0, minus 2, 0, 1, 0, 1, 0, 3. And there is some initial condition 0, 1, 0. So the goal is to find out what is e to the power at using the Cayley-Hamilton. Okay, so this means that this is the function f of a is e to the power at. Then we need to find out a reduced polynomial g of a or g of lambda. Right? So this will begin with figuring out the eigenvalues. So it's e to the power minus 5. Yeah, you can do that. Equals minus lambda, and then so we can do this. So this comes out to be lambda minus 1 squared, lambda minus 2 equals. Now let's see how we can actually adapt the theory which we have just learned, and find out what is equal to parity. So this is a third order system. We want to write this f of lambda in terms of some g of lambda, which will go to lambda to the power 2. So this is beta 1 lambda plus beta 2 lambda square. Okay. So let's say this is the first eigenvalue lambda 1. This is lambda 2. So f of lambda 1 would be g of lambda 1, beta 0 plus beta 1 plus beta 2. F of lambda 2 would be g of lambda 2. So 4 beta 2. And then this one gives another equation, right? So d by d lambda of f of lambda. Mm, At lambda equals 1 equals d by d lambda of g lambda evaluated at lambda equals 1. This means this is beta 1 plus 2 beta 2. This is simply beta 1 plus 2 beta 2. Okay, so now we have three equations. This is 1, 2, and 3. So we already know the right hand or the left hand sides. This, and this. Because f of lambda is e to the power lambda. So this is e to the power t. This is e to the power 2t. And just mix this is so this becomes simply again e to the power t. So just sorry, this is e to the power. So we have three equations. These are e to the power t equals beta 0 plus beta 1 plus beta 2. E to the power t equals beta 1 plus 2 beta 2. And then e to the power 2t equals beta 0 plus 2 beta 1 plus 4 beta. Okay, so this is can be written like let's say in a matrix form. This is beta 0, beta 1, beta 2. This is 1, 1, 1, 0, 1, 2, 1. Okay, so just if you have to find this out quickly, just check if this is invertible. So let's say this is some matrix M. This implies that this is M inverse M6. Okay. So I think the solutions would be not unique, right? This is a matrix equation of AX equals B. Right? Yes. So if A is invertible, then there's a unique solution. If it's not, then there would be two cases, right? Either there is no solution or there can be infinitely many. So, yeah, you can do it. Yes, okay. So beta is mu. I'll just write this down directly. M is invertible in this case. So there is a unique solution. This is minus 2 to the power t plus e to the power 2t. Beta 1 is 3t to the power t plus 2 to the power t minus 2 to the power t. Finally, beta 2 is so then we have f of a, which is e to the power at. This becomes beta 0 I plus beta 1 times a. That's what the 2 is. So you can substitute these in here and find out what e to the power at is. So I write this down directly. You can verify this later. So this is so. E. And now if we want to find the solution of x dot equals ax, we already know in the initial condition that was 0, 1, 0. So we multiply this. This means that we are selecting the second column of this matrix. So x of t is 0 e to the power t. So if you start from this initial condition, the first two states remain at the initial condition, but the second state just grows in time. Alright. Now let's move on to another section. This is controllability. Yeah. Okay. Alright. So now we have two tests to determine controllability. This is first one is the Kalman's matrix. So Kalman's matrix in which we find out this C matrix. This is script C. So this is B, and then we write AB square B till e to the power n minus. So this simply means that I'm just combining all of these and writing them down in the matrix C. So if the rank of this matrix is equal to order of the system, then we say that the system is controllable or the pair AB is controllable. And the next one is, just a second. And the next one is Gilbert's test. Yeah, sure. I think it's just so it all starts with the solution. So if we have, let's say, x dot equals ax plus bu, because now you want to talk about controllability, so there is an input. So x of t is so this is going to be t minus tau. Right. So let's say that the initial condition was zero, right? For linear systems, you can add any two states, right? That's why it's linear. So we can always assume that we're starting from some initial condition. X0 equals 0, 0, 0. Let's say for our third order system. So then this becomes 0. So x of t is simply 0t. Uh, so controllability for an LTI system means if you start from some initial condition, you can always reach any state of the system by some finite input u and some finite time t, right? So this means that we can get any x of t, let's say in the state space Rn. This means that they should exist, right? Yes, yes. So what it means that you fix some state that you want to reach here, and then you find out what you should be. So you start from x0. You say if it goes both ways. So it means that if you have u of t, you start from x0, you reach some, let's say u1, x1 of t. You get some other input for all time t equals 0 to some capital D. You get, and then you kind of span the whole space of all the states. Right? So you get some UN, maybe you get here. So this means starting from any condition, you can go anywhere in this space. This is controllable. And if you cannot, then it means the system is uncontrollable. It could be like you cannot go anywhere, or you could go to some states. That is partial controllability. So this should exist, right? This integral. And this means that, first of all, yeah, yeah. Yeah. That is still fine because the states might be dependent on each other, right? I think it would be, let's see, some second order system. Sorry, x plus 0, 1. And let's say this is x1, x2. This is 0, 1. Say 1, 2. So this, yeah. Yeah, yeah, you cannot. Yeah. If these were maybe, for example, just a simple diagonal matrix, then this means that this is simply x1 and this is what is controlled. Mm, okay, actually, we can check if this is A and this is B, the system is controllable, right? This is B and AB. Uh, AB is 1, 0. Okay. This is yeah, this is easy, right? A is identity in this case. AB is B. Controllability matrix is B and B. So what is the rank? Rank is either the determinant if it's a square matrix or a number of linearly independent rows or vectors. In this case, there is only one independent vector. Rank of C is 1. So only one of the states is linearly independent. One of the states is controllable. And you can actually see this. Only x2 is controllable, x1 is not controllable. And also in this case, x1 of t is t to the power t, x1 is 0. So it is also growing in times. If it was -1, then this, and if you could, it would not be unbounded system. It would still decay to 0 and you can control this too. So you get partial control. Okay, so back to this. So if we want, yeah, 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 yeah. Yeah. No, no, independent. This is not full or complete controllability. This is partial controllability. So partial controllability is the states which you can control. These are controllable, and which are not controllable, they should decay in time, right? It should not, those states should not become unbounded. So that is partial. That is also known as stabilisability. So I think you will get to know more about it. Okay, so back to this. If we want the system to be controllable, then it could be any state in Rn. This means that this integral should exist. This means that 0 to t. So this is, um, so I'm just going to expand the exponential in this case. So this is identity plus a t minus tau plus b square t minus tau square by 2 factorial and so on. This whole multiplied by p whole tau. So now you can actually see, right? Why is that the Kalman test? So first one is, yeah, yeah. This is AB, mm, T minus tau, tau. This means square B and so on, right? So this means if we are talking about an LTI system, A and B are constant, right? We can take this out of the integral. This is B, AB, and so on times this. Minus tau, d tau, and so on. This is what xt looks like, right? So this should be invertible so that you can find out what these are following this. So the rank should be full. That should be full rank. I think we can figure out what the dimensions are. Okay. Yeah, this is fine. Okay. So first one was the Kalman's test. Second one is Gilbert's test. In this, we use the eigenvalues or the diagonal form to comment on the controllability of the system. So step one in this case is to diagonalize using the modal matrix P or M, you can call it. Step two is that you get these diagonal forms. This is, for example, lambda 1, lambda 2 till lambda n. Let's say for now distinct eigenvalues. To get B bar is, I think, PB or P inverse B. You can just check this. And this comes out to be again a vector. So this is, I think this is P inverse B. So now the new state is, for example, Y. Y transform is Bx. This is Y dot Vy plus B. Now this means that we have a decoupled system, right? And if any of the entries are zero corresponding to that eigenvalue, then that state or the eigenvalue is uncoupled. Okay. And then there is a case for repeated eigenvalues, and we'll look at it. So for now, just a simple question. This is question 9. Let me just write this. If this is 0, then let's say this is kth entry, then kth is okay, yes. Yeah, this is I think this is along those lines because you are actually looking at the spectrum, not the frequencies or eigenvalues. These are all related. So determine the controllability of the following systems. So the first one is second order system. This is -2, 1, 1, -2. We also need B, so B is 1, 0. So all we need is B and AB. And now we have to figure out the rank of this matrix. So AB is, just do this, so this becomes -2 and 1. This becomes 1, 0, -2, 1. The determinant, this is a square matrix, so we just need to find the determinant to comment on the rank. Determinant is 1, which is non-zero, which implies that C has full rank, which implies that the pair AB is controlled. Now, another example is this. This is a third order system. A is -1, 0, 0, 0, -2, 0, 0, 0, -3. B is 1, 0, 1, 2, 3. Alright, so now there are two methods. This is already in diagonal form. We can use the Gilbert's test because the eigenvalues are exactly these are diagonal entries, or you can use the Kalman's test too. So C in this case is going to be B, A, B, and A squared B. So I'll write this down directly. This comes out to be 1, 1, 2, 0, 2, 1, -1 -2 -6 1 4 18 0 8 9. Okay. So now this is 3 by 6. This is not a square matrix, so you cannot calculate the determinant. So you need to find the rank of C is going to be less than or equal to minimum value of number of rows or columns, right? So this is going to be less than equal to 3. And we have 3 states also. So we need to find 3 independent columns, or what you can do is find out if these are 3 independent rows, right? So how do you do that? So this is, let's say, alpha 1 times the first row, the second row, and the third row. We equate it to 0, and if we get lambda 1 equals lambda 2 equals lambda 3 0 all simultaneously, then this means that rank is C. Oh, this is good. So you can compute this. This would result in, I think, this would be alpha 1 plus alpha 2 plus alpha 3 equals 0. And then you can select any of these equations to find out alpha 1 and alpha 2. Okay, so you can also use the Gilbert's test because these are distinct eigenvalues. And if any of the rows corresponding to that eigenvalue is 0, that means it's not controllable. But in this case, it is, right? None of them are completely 0. So the pair is controllable. So you can verify probability using either Kalman's test or Gilbert's test. Okay. So now let's look at some already diagonalized system. And let's see if we can apply Gilbert's test to comment on controllability. So first one is x1 dot x2 dot equals -1 0 0 -2 x1 x2 plus 2 5. So none of the rows are 0. So AB is controllable. Alright. Now let's look at a case of repeated eigenvalues. And we'll consider a larger system. So x1 dot x2 dot till x5. This is -2 1 0 0 -2 1 -2. Now 3 repeating eigenvalues are -2. And then 0 0 0 0 here, all zeros here. And then 2 repeating eigenvalues at -1 times this x vector plus this is going to be, so there are 2 inputs. So this is going to be 5 by 2, right? Okay, so this is 0 1 0 0 3 0 0 0 and 1. So I'll just write down the rule and then we can check. So for the case of repeated eigenvalues, of the elements of any row of B. So in this case, I'm going to name this B tilde. This is the diagonalized system. That corresponds to the last two of each Jordan block. So what I mean to say is that, for example, this is the first Jordan block. These will have three entries in the B data matrix. This is all this. And then we look at the last row. If it is all zeros, then it's not controllable. If it is not zero, then it is controllable. This is for the first Jordan block. For this, we have this. This is zero, but we have to look at the last row. And this is not zero. So this means that the pair AB is controllable. So let's look at another example. So this is C. This is x1 dot x2 dot minus 1 0 0 minus 2 x1 x2 plus 2 0. These are distinct eigenvalues already diagonalized. This does not have a control, so not controllable. Then the last one is x1 dot x2 dot x3 dot. We have repeated eigenvalues at minus 1. This is the vector x. So two inputs, u1, u2. This would be 3 by 2, 4, 2, 0, 3, 0. So for this block, we have this block and the last row is 0. So this means that the pair is not controllable. Yeah, it is like, but it's not correct. We actually have to do some more tests to figure out if it is actually controllable. It might be the case that if you have some A and B matrix and you input that in the controllability function in MATLAB, and that actually says that the rank is infinite or there is singular. That's how you know that there is no control. Now we look at stabilisability. This is the last section. Stabilisability for partially controllable systems. So this means that the unstable modes, the unstable modes are controllable. So we can damp them or we can control them however we want. And the stable modes, the stable eigenvalues, those are uncontrollable. And these would eventually die down and we can control these ones. So let's look at an example. x1 dot x2 dot 1 0 0 minus 1 plus 1 0. So this is already in diagonal form. This is unstable. Corresponding to this, there is a control signal. So we can actually inject some control. This is a stable eigenvalue or stable mode. This can have a control or not, but in our case it is not. So this is fine. It will eventually die. This would be x2 dot equals minus x2. And the differential equation solution is simply stable. So this means that again the pair AB is stabilizing. Alright, so that's it for today. If you have any questions, you can ask me now. If not, we can meet in the next session. Yeah. Yeah. Mm, yeah. Uh, uh, okay, so I think in that case, let's say there is some disturbance and there is a vector associated. Okay, so it's x dot equals ax plus bu. That's how we evaluate a control plus, let's say, e times disturbance d. Okay, so for a second order system, this would be something a1 into a4 x1 x2. Let's say b1 b2 times u of t plus even some constants d of n. This is a scale. So let's say this is some noise or disturbance, right? So now you want to know what would be the effect of disturbance, right? Mm, Controllability would just be for the controls that we can inject in the system. So that would be for this matrix. This would be the B in the Kalman's test, not the disturbance. Yeah. Yeah. Right.